So, good morning, everyone. We are the Group 4 of ABS-CHPC, and we will be discussing the topic traffic flow characteristics. To start, we have here the lesson objectives, and we have to define the traffic flow and its types, the characteristics of the traffic stream, establish the relationship between the traffic stream parameters, and then calculate and compute parameters with given data. Now let us define traffic flow. So it is also known as the traffic stream that is made up of individual drivers and vehicles interacting in many ways with each other and then elements of the roadway in general environment. Because the judgments and abilities of individual drivers come into play, vehicles in the traffic stream do not and cannot behave uniformly. So traffic flow is basically the total number of vehicles passing a given point in a given time, and traffic flow is expressed as vehicles per hour. So we have two types of traffic flow. The first one is the uninterrupted flow. So it is a traffic stream that operates free from the influence of traffic control devices as signals and stop signs. And the other one is the interrupted flow. So unlike the uninterrupted flow, here we have signals and stop signs which influence the traffic stream. The next one is the traffic stream parameters. So this can be mainly classified as the measurements of quantity, which includes density and flow of traffic, and measurements of quality, which includes speed. So this is basically the analysis of the performance of a highway. And there are two traffic stream parameter measures. These are the macroscopic and the microscopic. And later on, we will discuss these two briefly. So what is macroscopic measures? So traffic flow, speed, and density are variables that form the underpinnings of traffic analysis. We begin the study of these variables with basic definition of traffic flow. Speed and density must be presented. So macroscopic measures describe the traffic stream as a whole. Here we have one of the variables, which is the traffic flow. So traffic flow is defined as Q is equal to N over T, where Q is equal to the traffic flow in vehicles per unit time, and then N is the number of vehicles passing some designated roadway point during the time, and T is the duration of time interval. So the second variable of macroscopic is the speed. So the average speed is defined in two ways. We have the timing speed and then the displacement speed. The first is the arithmetic mean of the vehicle speed observed at some designated point along the roadway. This is referred to as timing speed and expressed as the timing speed is equal to the summation of the numbers. The t is equal to 1 multiplied by the spot speed over n. Next is space mean speed. This measure of average traffic speed is referred to as the space mean speed and is expressed as Vs is equal to L over T, while Vs is equal to the space mean speed in unit distance per unit time. Then L is the length of roadway used for travel time measurement of vehicles. And then T is the average vehicle travel time defined as T is equal to 1 over N multiplied by the summation of the numbers, where the imaginary number is equal to 1 multiplied by Ti, where Ti is equal to time necessary for vehicle I to travel a roadway section of length L, and N is the number of measured vehicle travel times. Substituting equation 4 into equation 3 yields Vs is equal to L over 1 over N multiplied by the summation of N, and where the imaginary number is equal to 1 multiplied by Ti, or Vs is equal to L over 1 over N multiplied by the summation of N, and the imaginary number is equal to 1 multiplied by 1 over L over Ti. Then this is the harmonic mean of speed, or the space mean speed. The space mean speed is the speed variable used in traffic models. So here we have a sample of problem for time and space mean speeds. The speeds of 5 vehicles were measured with radar at the midpoint of a 0.5 mile section of roadway. The speeds for vehicles 1, 2, 3, 4, and 5 were 44, 42, 51, 49, and 46 miles per hour respectively. Assuming all vehicles were traveling at constant speed over this roadway section, calculate the time mean and the space mean speeds. Here is the solution for our problem. So for the time mean speed, we're going to use the equation 2. And as mentioned a while ago, this is the formula for the time mean speed. We're just going to substitute the given in the formula. So we have the time mean speed is equal to the summation of all the vehicle speeds over the total number of vehicles, which is 5, because we have 5 vehicles. And this will give us 46.4 miles per hour. And that is our time mean speed. For the space mean speed, we're going to use the formula for that as well. We're just going to substitute the given. So we have the space mean speed is equal to 1 over n multiplied by the reciprocal of the vehicle speeds. So we have the time mean speed is equal to 46.17 miles per hour. So we have to note that the space mean speed will always be lower than the time mean speed, unless all vehicles are traveling at exactly the same speed, in which case the two measures will be equal. So for the last variable for the macroscopic measures, we have the density, or K. It is sometimes referred to as the concentration, and is defined as K is equal to N over L, where K is equal to the traffic density in vehicles per unit distance, and then N is the number of vehicles occupying some unit of roadway at some specified time, and L is the length of the roadway. So the unit length is usually 1 mile, thereby making vehicles per mile, or VH per MI, is the unit of density.
The other category under the traffic stream parameters are referred to as microscopic measures. These measures or parameters describe the characteristics of particular pairs of vehicles in a traffic flow. The figure shown illustrates the types of microscopic measures, namely the headway or time headway, gap, clearance, and spacing or space headway. Time headway. Time headway is the difference between the time that the front of a vehicle arrives at a point on the highway and the time that the front of the next vehicle arrives at the same point. We can measure the time headway between two vehicles by starting a chronograph when the front bumper of the first vehicle crosses the selected point, and subsequently recording the time that the second vehicle's front bumper crosses over the designated point. The time headway is related to t, usually expressed in seconds as defined in equation 1 by t is equals to the summation of I equals 1 to n of h sub I, where t is the duration of time interval, h sub I is the time headway of the ith vehicle or the elapsed time between the arrivals of vehicles I and I-1, and n is the number of measured vehicle time headways at some designated roadway point. Substituting equation 8 into equation 1 gives q is equals to n all over the summation of I equals 1 to n of h sub I, or q is equals to 1 over h bar, where h bar is the average time headway or h sub I over n in unit time per vehicle. This is now the equation for the time headway. Next is spacing. Spacing, usually expressed in feet or meters, is the physical distance between the front bumper of the leading vehicle and the front bumper of the following vehicle. Spacing complements headway as it describes the same space in another way. The individual spacing between successive vehicles can also be related to the density. The roadway length L in equation 7 as shown can be defined as L is equals to the summation of I equals 1 to n of S sub I, where S sub I is the spacing of the ith vehicle or the distance between vehicles I and I-1 measured from front bumper to front bumper, and n is the number of measured vehicle spacings. Substituting equation 11 into equation 7 gives k is equals to n all over the summation of I equals 1 to n of S sub I, or k is equals to 1 over S bar, where S bar is the average spacing or the summation of S sub I over n in unit distance per vehicle. This is now the equation for the spacing or space headway. Another type under microscopic measures is the gap. Gap is very similar to time headway, except that it is a measure of the time that elapses between the departure of the first vehicle and the arrival of the second at the designated point. Gap measures the time between the first vehicle's rear bumper and the second vehicle's front bumper, whereas headway focuses on front-to-front times. The gap is commonly measured in seconds. Lastly, the clearance. Clearance is similar to spacing, except that the clearance is the distance between the rear bumper of the leading vehicle and the front bumper of the following vehicle. The clearance is equal to the spacing minus the length of the leading vehicle. Clearance, like spacing, is often measured in feet or meters. Based on the definitions presented, a simple identity provides the basic relationship among traffic flow, speed or space mean, and density, denoting space mean speed, V bar sub S as simply V for notational convenience. The relationship is defined as Q is equals to V times K, where Q is the flow, typically in units of VH over H, V is the speed or space mean speed, typically in units of miles per hour, and K is equals to density, typically in units of VH over miles. Because flow is the product of speed and density, the flow is equal to zero when one or both of these terms is zero. It is also possible to deduce that the flow is maximized at some critical combination of speed and density. Two common traffic conditions illustrate these points. The first is the modern traffic jam, where the number of vehicles are very high and the speeds are very low, as shown in the animation below. The second condition occurs when the number of vehicles are very low and drivers can obtain free flow speed without any undue stress caused by other vehicles on the roadway. The extremely low density compensates for the high speeds. Sample problem for speed-flow-density relationship. Vehicle time headways and spacings were measured at a point along a highway from a single lane over the course of an hour. The average values were calculated as 2.5 seconds per vehicle for headway and 200 feet per vehicle or 61 meters per vehicle for spacing. Calculate the speed and average speed of the traffic. To calculate the speed of the traffic, the flow and density need to be calculated from the headway and spacing data. Using equation 10, Q is equals to 1 over the average time headway gives the value of flow, which is equal to 0.4 vehicle per seconds. The data were collected for an hour, which gives the value of flow equals to 1,440 vehicles per hour. Meanwhile, density is determined using the equation 13, K is equals to 1 over the average spacing, which gives the value of density equals to 0.005 vehicles per feet. Or, applying this spacing over the course of 1 mile gives the value of density equals to 26.4 vehicles per mile. Now, rearranging equation 14 to solve for speed gives V is equals to Q over K. Substituting the value of Q and K into the equation gives the value of speed, which is equals to 54.5 miles per hour. For the average speed of traffic, we can determine it directly from the average headway and spacing values. So, average speed is equals to the average spacing over average headway, which gives the value of 80 feet per second or 54.5 miles per second.
Next is the macroscopic models of traffic flow. In simple terms, these models represent the relation between the speed and density. The first and most simple relation between them is proposed by Greenshields, which is the Greenshields model. Greenshields, or Dr. Bruce Douglas Greenshields, was a prominent traffic researcher. He proposed this model in 1935. The Greenshields model assumed a linear speed-density relationship as illustrated in figure number 2. The equation to describe this is V is equals to V sub f minus the quantity V sub f all over J sub k times k, where k is the density, V is the mean speed at density k, V of sub f is equals to the free flow speed, and k sub j is the jam density. This equation means that when the density becomes zero, speed approaches the free flow speed. In figure number 3, we can see the relation between the speed and flow. In figure number 4, we can see the relation between the flow and density. Once the relation between speed and flow is established, the relation with flow can be derived. As shown in figure number 4, the relation between flow and density is in parabolic shape. From the speed-flow-density relationship discussed a while ago, we know that Q is equals to V times K. So substituting equation 15 in equation 14, we get the equation Q is equals to V sub f times K minus the quantity V sub f all over K sub j times K squared. So finding the relation between speed and flow, we put k is equals to q times v in equation 15. And then we got the equation q is equals to k sub j times v minus the quantity k sub j all over v sub f times v squared. This relationship is again parabolic as shown in figure number 3. And once the relationship between the fundamental variables is established, the boundary conditions can be derived. The boundary conditions are k sub j or the jam density, the free flow speed or the v sub f, and the maximum flow or the q max. To find the density at maximum flow, we differentiate the equation 16 with respect to k and equate it to 0. Solving, we get the equation k is equals to k sub j all over 2. And denoting the density corresponding to the maximum flow as k sub 0, we get the equation k sub 0 is equals to k sub j all over 2. From this, we know that the density corresponding to the maximum flow is half the jam density. So once we get the k sub 0, we can now derive the maximum flow or the q max. So substituting equation 18 and equation 16, we get the equation q max is equals to v sub f times k sub j all over 4. Thus, the maximum flow is 1/4 the product of the free flow speed and the jam density. Finally, to get the speed at maximum flow or the v sub 0, we substitute equation 18 and equation 15. Solving this, we get the equation v sub 0 is equals to v sub f all over 2. Therefore, the speed at maximum flow is half of the free flow speed. Next macroscopic model was proposed by Joseph Greenberg, which is the Greenberg's logarithmic model. Greenberg used the fluid flow analogy concept and proposed a logarithmic speed-density relationship, which is shown in figure number 5, and it is also shown in the equation v is equals to v sub 0 times the natural log of the quantity k sub j all over k, where k is the density, v is the mean speed, k sub j is the jam density, and v sub 0 is the speed at maximum flow. This model has gained good popularity but is also critiqued for its inability to predict speed at lower densities, because as the density approaches 0, speed tends to increase to infinity. Its another drawback is it violates the boundary condition. Zero density can only be attained at infinitely high speed. The next model is the Underwood's exponential model. Underwood tries to overcome the limitation of Greenberg's model by putting forward an exponential model. Figure number 5 shows the Underwood's speed-density relationship. And the equation for this relation is v is equals to v sub f times the quantity negative k all over e raised to k cre, where v sub f is the free flow speed and k cre is the critical density. This model calibrates the free flow speed and the critical density, but it has its main drawback that speed only becomes 0 when density reaches infinity. Hence, it cannot be used for predicting speeds at high densities. And the last model for macroscopic, the Pipes generalized model, introduced a new parameter n and provided a more generalized modeling approach. Pipes proposed the model shown by the following equation: v is equals to v sub f times a quantity 1 minus k all over k sub j times n. Next, we proceed to the microscopic model of traffic flow. Microscopic traffic flow, in simple terms, attempts to analyze the flow of traffic by modeling driver-to-driver and driver-to-road and interactions within the traffic stream. An example of the microscopic traffic flow was proposed by the French mathematician Simeon Denis Poisson, which is called the Poisson model. Poisson model is an example of the models that account for the non-uniformity of flow that are derived by assuming that the pattern of vehicle arrivals corresponds to some random processes. This model is expressed as the P of n is equals to lambda times t raised to n times e raised to lambda times t all over n factorial, where P of n is equals to the probability of having the n vehicles arrive in time, lambda is the average vehicle flow or arrival rate in vehicles per unit time, t is the duration of time interval over which vehicles are counted, and e is the base of the natural logarithm, which is equals to 2.718. The assumption of Poisson vehicle arrivals also implies a distribution of time intervals between the arrivals of successive vehicles, time headway. To show this, note that the average arrival rate is lambda is equals to q all over 3,600. Lambda is the average vehicle rate in vehicle per second, q is the flow in vehicle per hour, and 3,600 is the number of seconds per hour. Substituting equation 24 to equation 25 give us the equation P of n is equals to the quantity Q times T all over 3600 raised to n times E raised to negative Q times T all over 3600 all over n factorial. Note that the probability of having no vehicles arrive in time interval of length is equivalent to the probability of vehicle headway being greater than or equal to the time interval. So from equation 26, we get the equation P of 0 is equals to E raised to negative Q times T all over 3600. Distribution of vehicle headways is known as the negative exponential distribution or simply exponential distribution. Poisson model has its limitation also. Its primary limitation is the constraint imposed by the Poisson distribution that the mean of the period observation is equal to the variance. In figure number 7, we can see the exponentially distributed probabilities of headways greater than or equal to t, with q is equal to 360 vehicles per hour.
Queuing theory. Queuing theory can be used to analyze the flow of traffic on the approach to and through an intersection controlled by a traffic signal. This is accomplished by analyzing the cumulative passage of vehicles as a function of time. The formation of traffic queues during congested periods is a source of considerable delay and results in a loss of highway performance. Given this, it is essential in traffic analysis to develop a clear understanding of the characteristics of queue formation and dissipation along with mathematical formulation that can predict queuing-related elements. Moreover, the impact of queues on performance and productivity has led to numerous theories of queuing behavior, such as the process by which queues have been formed and dissipated. As been shown, the models of traffic flow presented earlier, such as the macro and microscopic models, they will form the basis of studying traffic queues within the more general context of queuing theory. In this slide, we can see the queuing diagram for interrupted flow. It shows the flow of one intersection approach. Traffic is stopped from the time 1 to time 2 during the red signal interval. At the start of the green interval, traffic begins to leave the intersection at the saturation flow rate and continues until the queue is exhausted. Thereafter, the departure rate is equal to the arrival rate until time 3, which is the beginning of the next red signal. At this point, the process starts over. Now we have the traffic flow characteristic studies. For the example study 1, we have the traffic flow characteristics for multi-lane highway in India, authored by Jain and Singh. The traffic composition of multi-lane highway in India comprises of a wide range of vehicles in terms of their type, size, engine power, maneuvering ability, and etc. This mix of vehicles with different operating capabilities result in a broad range of speed. Slow-moving or non-motorized vehicles occupy the lower range of speed spectrum. To understand the real traffic behavior, it requires quantification of some of the basic traffic flow characteristics, such as speed, flow, density, and occupancy, through which the capacity can be derived. The main objective of the study is to estimate the basic traffic flow parameters for 6-lane divided traffic stream under the study and to evolve speeds flow relationship for different vehicle types. In the present study, linear models have been developed for speed flow equation for different vehicles on each lane on selected road sections of 6-lane divided carriageway. In this study, we have two conclusions. One is that on 6-lane carriageway, the traffic flow is quite significant as compared to lane adjacent to shoulder. And two, by close looking at the speed flow relationship developed exclusively, it is based on traffic speeds and flow with the outermost lane that reveal that the speed of vehicles on this lane is very low even in free flow conditions. For the next study, we have the flow characteristic and traffic stream modeling on Indian Expressway, a case study of Mahatma Gandhi Expressway by Jabina, Gurang, Srinivas, and Kayitha. In this study, they attempted to analyze the traffic stream characteristics and to model traffic flow by taking two roads connecting 4-lane divided expressway. This analysis of traffic stream characteristics will provide basis for planning, designing, and operating management of expressway in future. The required traffic parameters are extracted from these frames manually for better accuracy. Moreover, The developed traffic flow model showed linear and exponential speed density relationship along with parabolic speed flow and flow density equations, which is in other words, this tells or indicate a free speed with optimum density, jam density, and capacity. Based on the results of this study, capacity estimates are proposed for a 4-lane divided expressway and then will result to be very useful for the practitioners and also for the ongoing efforts to prepare for highway capacity manual.
And that concludes our report. Thank you so much for listening.